Okay, so there was one question which maybe other people are interested in. So the question was, if you run over 5 minutes on your presentation, what happens? Okay, I'm going to ring the bell at 5 minutes and I'll have to cut you after 7. So this will be absolute maximum, because we would like to leave as much time for questions as well. And please, this is just kind of a fun activity, so please everyone ask questions from the presenters. If you have not, if you have any questions, if you haven't seen that before, and anything else on what they present. So today I will actually show you some experiments, since our lectures are on tabletop experiments, so I'll show you some scheme. But then we also talk about mainly two things. First, how you actually detect this ultralight dark matter. And we will do actually two cases. We'll do the scalars and we'll do the axioms. And there are too many experiments. I can't show you all experiments, but I'll show you scalar experiments with clocks. And the second thing, we'll actually talk about some of the technologies. Because while collaborating with particle physicists, me being AMO theory, we also found that in many cases we need to know at least some technical details of the experiment. And I collaborate with my experimental colleagues as well. So we'll just discuss enough experiments, experimental details, so we need to know in order to understand how narrow band or broadband range we can actually get for the dark matter masses. So we'll go into some technical detail. And we also, I will answer you the question of what's the difference between clocks and interferometers. So how in principle they work, because now they're using pretty much the same systems at this point. Okay, so we'll start with clocks and talk about the dark matter searches with atomic, molecular, nuclear clocks. I have to give you a disclaimer. Out of all those three clocks, pretty much what really works well right now are atomic clocks. So, and the difference between the three is that it's pretty much exactly what it sounds. In case of atomic clocks, the transitions which we are using to search for dark matter are based in transitions in atoms. It's between different atomic energy levels. In molecules, are between different molecular levels, and in nucleids, between different nuclear levels. And there's only one nuclear, thorium-229, for which that actually works. And I first would like to give, I didn't connect this, a reminder of how we actually detecting dark matter with clocks. So we discussed yesterday that if there is a scalar field and it couples to standard model, presumably if it couples to standard model, it probably couples to the entire standard model. And maybe it couples to muons and neutrinos as well, but in atoms, we pretty much are stuck with electrons, quarks, and gluons, and photons. So those are the ones we should be talking about. Mostly we'll be talking about photons in this case. So what actually happens, let's review. The dark matter field couples to electromagnetic interaction and normal matter. And that's the Lagrangian we described before. So if it does, it will make fundamental coupling constant oscillates and mass ratio oscillates. Again, this is a very default dilatonic coupling. You in principle can get it for relaxion. If you're coupling to Higgs, you can actually get the same effects as well. Even you get some other effects for that. So this is a very, very default dilatonic type coupling. We actually look at linear coupling, but the logic for the quadratic coupling, it's exactly the same. All the derivations are exactly the same. You just get phi squared over lambda squared. The problem is that this is suppressed over the linear coupling. So in all the theories, when you actually have a measurable effect quadratic coupling, you pretty much have to suppress the linear one. And you can do it via some symmetries. So there is a recent paper on arXiv with Gilad Perez group and my team of actually what those specific cases are. So we actually looked at what differentiates whether you will see linear or quadratic couplings. Okay, so now your fundamental constants oscillate, mass ratios oscillate. And the reason why I say mass ratios is because in order to separate units out, we would like to look at variation of dimensionless constants. And the typical dimensionless constants for the masses, it's ratio of electron and proton mass, just because it naturally arises in atomic and molecular energy levels, and the quark mass to lambda QCD. Now, no, not people are not entirely happy with the last one, but that seemed to be naturally arising if you uh, have the fundamental constants variation in the nuclei. Okay, then all of the energy levels oscillate, and therefore the clock frequency oscillate. And the critical point that if all the atomic levels or nuclear levels depended the same way, this would be invisible. So the critical reason why this works as a detector is that the strength of the sensitivity to those effects depends on which transition that is. And with atoms, the very simple rule is that the heavier the atom, the larger the effect, but there are some additional enhancements. So in fact, the lighter or heavier, so the lighter or heavier, and I mean the nuclei in this case, because of course all the mass of an atom is mostly in your nuclei. This effect can get you from, say, 0 to 1. In order to get, say, 100, you really need to do something else and look at some very specific systems. Okay, so now, because the strength of the effect depend on transition, also the cavity length would oscillate. And you can ask, well, we are talking about clocks. Why do I care about the cavity? It's because ultra-stable lasers have cavities inside them. There's a physical, well, like maybe 30 centimeter or so cavity, and the lasers actually get stabilized to cavity. So you pretty much get 2 for 1. You have cavity and the atoms in the same system, so you can compare it both. And then what you do, you monitor ratio of clock frequencies over time, or clock to cavity, and you would like to make, of course, the dependence of these sensitivities for 2 clocks as large as possible. Also, sensitivity can be either positive or negative. It doesn't have to be all positive. It's completely, in this case, you can compare it to clocks, and in some case, the energy levels structure reverses, and the positive sensitivity goes to exactly the same one, but negative. That's kind of the best case scenario. So, and the question is how broadband. I will show you naturally why the sensitivity go pretty much somewhere between 10 to the minus 21 to about 10 to the minus 12. And that literally goes from the nature of clock operation, and also by that time, your measurement time is just too long, because 10 to the 6 second is still okay, 10 to the 8 seconds is 3 years. And also by this time, we already run into astrophysical limits for it to be 100% dark matter. And now we'll get to more specifics as which fundamental constants are we actually sensitive to. So we'll talk a little bit about today, but I want to review it now. So any questions on what exactly are we doing here? Okay. So the first case, optical transitions. Okay, when I say optical transitions, different people sometimes mean different things by that. So let's discuss. What generally is meant is that the difference between levels is in somewhere sort of near the visible part of the spectrum. Generally, it also means it's accessible by tabletop ultra accurate lasers. So generally, people refer to it, even though the visible case, it's about 400 to about 750, or generally anything from 150 nanometers to 1500 nanometers, it's somewhere within that range. So mainly for neutral atoms or not too singly charged atoms, that means the transition is between 2 different electronic states. Not the hyperfine structure, not the fine structure, but different electronic substates. And one of the example, for example, would be 5s square, 5s, 5p in strontium. And this is 3p0, 1s0. So in this, the difference, it's a few hundred nanometers. So that's kind of what we want. The absolute requirement for the clock, the absolute requirement, this state has to live for significant time. And significant time, it's at least a few seconds, which means the electric dipole transition must be forbidden. And that means there are very specific atoms in which you can build the clocks. You can't build the clocks from just any atom. The simple rule, if you can build a quantum computer from this, you can build a clock, because quantum computing requires longer memories. It's exactly the same requirement as for the qubit. So the state has to emit a stable. And by the way, let's see the transition. I'm going to tell you the designations, and let's see how people remember the quantum mechanics. Okay, so the S means L is 0. Here this S means L is 0. Here it means the spin is equal to 0. This means angular quantum number, total angular momentum is 0. That means L is 0 for this electron, L is 1 for this electron. And this 2 means we only care about 2 electrons. So the strontium, it's alkaline earth. It's in the second line, second column of the periodic table. So there are 2 electrons outside of closed shells. We don't care about the rest of them for these purposes. They're all closed shell, angular momentum is 0. And now spin is 1, L is 1, J is 0. Who can tell me, just from looking at it, why the state lives for a long time? Anyone remember selection rules? There's one glaring here. So J0 to J0 transition are extremely forbidden. So angular momentum 0 to 0, electric dipole transitions pretty much cannot occur. So the other thing in which to look for, so this is kind of an absolute rule, the 0 to 0. You pretty much need a 2-photon transition to make this happen, or you have to, so the other thing, you can, the one reason why it becomes allowed, if you have strontium 87, then you actually have a nuclear spin, I think of 7 halves, and that will bind to J0, and that actually will make it weakly allowed just because you're coupling it to nuclei and you're actually splitting those levels. But again, that's a very weak effect. Or you can put magnetic field on. And as I said, those are transitions which live for more than 100 seconds. That's what we want. So again, why do we care if it's 1 second or 100 seconds? The stability of the clock critically depends on how long-lived the transition is. So, and this is a irreducible problem. So let's say you can build an extremely precise clock, like 10 to the minus 20, significantly better. So all of your uncertainty are completely controlled. It's not, the environment essentially not touching it. But if the lifetime, if this level of decay, if the lifetime is not long enough, it will take you forever, essentially a decade, to actually reach the 10 to the minus 20 to integrate. So the stability and the lifetime of the state essentially lead to the fact that you can reach your ultimate uncertainty much, much faster. There are many other things, why is it so? But this is the one you can't fix. So a lot of other things you can just increase some experimental parameters. This one comes with your atoms. Therefore, there are very, very specific systems out of which you can build clocks. And these systems actually are well known. So you cannot build anything from alkalis. And this is 1 electron. This is the first line of a table. So your, for example, things like sodium, potassium, rubidium, cesium, francium. I'm going to omit hydrogen. We don't care about hydrogen here. Okay, so out of this case, there are no metastable states for any of them. The reason why you can build qubits of them, with qubits, you actually can use a ground state for the microwave transition, but there you actually rotate it through the upper state. That does not work for clocks. You need direct optical transition here. So none of those work. However, for the next case, magnesium, then calcium, strontium, and barium, radium. Radium doesn't have a stable isotopes, neither does francium, so technically it's possible, but you pretty much have to be the radioactive facility, which you don't want to be. Technically, you can build clocks out of any of them. For many reasons, strontium is one of the best ones. And not that you totally don't want this, but strontium has convenient lasers and some of the other properties. People have actually, there is progress with magnesium and calcium. And also the one which is kind of in this case is also ytterbium. The reason why ytterbium has 2 electrons above the closed shell is because ytterbium is it is a lanthonide, so it has 4f shell closed. And in this case, it actually has a similar structure, even though it's like in this part of the periodic table. Okay, so and those now have 1 valence electron, those have 2 valence electrons. It turns out to be, if you actually remove one of the electrons, this also works. Out of those systems, all of this work. And also the aluminum plus. So now, technically, this one has also 2 electrons, this has 1. So I'm mixing a little bit, actually. Let's put aluminum in there. Okay. And in this case, what actually happens that there is a difference between structure here and here. So again, 1 electron everywhere, 2 electrons everywhere. The levels reverses. So usually in alkalis, the levels go as S, P, and Z. When you remove 1 electron, the D goes here. And again, who can tell me why this transition is automatically long-lived? So S means the angular momentum of this electron is 0, D means angular momentum is 2. Again, that's basic quantum mechanics. Go ahead.
Because delta L is true, so L from L equals 2 or L equals 0 is forbidden.
Why? Tell me. Which selection rule? You're completely right, this is forbidden. But why?
It's forbidden for as a dipole transition.
Yes, it's not a dipole transition, but why is it not a dipole transition?
Because the variation of L is more than 1.
Yes, variation of L is more than 1. Technically, this is not entirely so. So you're absolutely right, but generally, this actually goes by J and not by L. So technically, you can actually have D3 half and S1 half. So variation of J is actually 1, but it's still forbidden. The reason why it's forbidden is because this both are parity even. Electric dipole operators parity odd. So it's literally because it's 0 to 2, it's even to even, and that actually goes by the angular momentum number. So an electric dipole operator only connects even to odd and odd to even. So the great thing that you can like literally just look at the electronic structure and you can tell whether it's a good clock or not immediately. Maybe some other reason why it's not a good clock, but this is enough. It gets slightly more complicated when a number of electrons increase. But generally a rule, if electric dipole transition has to be forbidden for the clock. So now other transitions are allowed. For example, the one which is allowed here is electric quadrupole. An electric quadrupole is allowed because delta J is less than 2, and electric quadrupole selection rules even to even. So as you see, there is already some atomic physics which goes into that. And generally for the clock development, you need to know the properties of those systems really, really well. And that's something which my team also computes. Okay. What other systems make good clocks? So here, as you see, those are ionized. So 1 electron is removed. You can continue to remove electrons. The problem with this is that generally all transitions very immediately go to ultraviolet and run outside of this range to the UV and then to X-ray. However, there are accidental exceptions because when you remove electrons, the electronic structure starts changing. So stuff like praseodymium, for example, 9+, californium 15+. So as you see, when you start removing somewhere between 9 and 15 electrons, you again run into the case when you actually can have a clock transition. There are some difficulties there because you don't have cooling transitions, but people figure out how to use those. So there's the first prototype of the highly charged ion clock. it already clearly looks like a complication. Why would people care? The reason why they care, it's unfortunately out of all of those systems from which people build high precision clocks, the only one which has sensitivity of 6 is Ytterbium Plus. The rest of them have sensitivity between 0 and 1. So there is no enhancement. So highly charged ions can have sensitivities up to about 100 or more. So in the sensitivity of 100, and I'll show you exactly how that's defined, means that if you build your clock with exactly the same precision, your dark matter search is 100 times better. So technologically, you don't need to build better clock, you just need to use a better system. And as you see, there is a lot of already atomic physics consideration, and there are also which specific electronic structure you pick, and the great things about atom, and that's in part why those atomic quantum sensors advance so quickly, it's because there are possibility to extremely high rate and very accurate theory predictions in this case. And in this case, why that matters? It matters because if you need to know property of an atom, experimentalists generally needed to, for example, figure out which lasers to build or to buy in order to find this transition or in order to actually build traps for these atoms. If you theoretically can predict those, it actually takes much less time to look for those transitions or to actually understand systematics for those clocks. And here the prediction can be as good as better than 1%. And the theory can actually guarantee the accuracy. Not for all of the atoms, but generally for those ones which are on the left side of periodic table, the accuracy is the best because there is least number of valence electrons, and also for some of the highly charged ions. Questions? Yes?
So about the lifetime of the metal saving, is it the longer the better, or is there some...
Okay, that's an excellent question. Generally, the longer the better, up to a point. Because honestly, we will have to say that besides this, so this is irreducible problem. But generally, the reason why you want a longer lifetime, it's because you would like to keep atoms in superposition. I'll show what it means for as long as possible. And they can't decay during that time. Your problem is that your laser is also your restriction. So the laser should remain stable and remain on phase during the whole time because it doesn't talk to atom during that time. So it's your laser actually stability, which eventually is actually worse than atoms. So right now the laser is good to a few seconds, but eventually can be to 100 seconds. So while the laser goes off phase, there are exactly 2 of them in a world right now. So you can, however, use a lot of tricks to fix the laser problem. You can't use tricks to fix the atom problem. So in this case, technically in the future, when we have better lasers and better quantum algorithms to actually operate those clocks, we could probably use much, much longer probe times. And that means we can actually get to the better accuracy faster. But the problem, for example, this Ytterbium Plus, that lives for 10 years. Now that means they actually have to use separate specific tricks because you need to pump a lot of power in the system to make this transition happen. So in that creates a bit of complication. So the other complication creates that if that atom is new and never been measured, and believe it or not, after 100 years of quantum mechanics, we don't know a lot of atomic properties, even basic properties. For all of those highly charged ions, we don't know any energy levels. We don't know anything experimentally about the system at all. So, and if transition leaks for a very long time, it means it's very, very weak. It means experimentalists have to literally scan the entire range where it possibly can be, and the scanning time could be years. So if it's very long, that becomes a problem. So over an hour becomes a problem. For the nuclear clock, that's why I've been looking for transition for 10 years, just because it looks like it's maybe a few hours. So in principle, experimentally, so it's kind of both an experimental problem that we are not actually using the entire lifetime because our lasers are not good enough. But eventually, you run into problems that if you actually knew where the transition was, it wouldn't be a problem, but it's really difficult to find it. Other questions? Yes?
As far as I know, you count how many atoms have changed at the double transition, right?
What?
As far as I know, you have to count how many atoms have done transition.
Oh, no. You count atom numbers. I will show exactly how that works.
Ah, okay, you sure?
Yeah, I will go through the procedure.
It influences
You can do it with one atom. So with ions, all of the ions right now operate with a single ion. Because unfortunately for ions, well, if you put a lot of ions in a trap, they start jittering because there's a Coulomb interaction. And the way you trap them, there is a little bit of jittering. The more ions you put in, the more they jitter, just because on how the trapping actually for ions work. So then we actually just have a paper on arXiv how actually do it with 1,000 ions, but for now all ion clocks are still operating with a single ion. And that's a bit of a problem. With neutral atoms, people can do the 100,000 right now, but they're not actually using entire 100,000. But what, maybe you ask specific question and I'll see if I can answer it, make sure. Okay, we'll get to that point. But first I wanted to show like which systems can be used for clocks. Okay. Anyone else? Okay. So optical transitions, what constants are we actually sensitive to? First, all of the transition, any transition are always sensitive to variation of alpha, of fine structure constant. For the simple reason that every energy level somewhere has a Rydberg constant in it, or it has some sort of Coulomb interaction. So anytime you can actually control anything by light, it means there is a Coulomb interaction involved, and you can always test for alpha. Specifically, if you look, your frequency is proportional to the Rydberg constant at infinity, and then some sort of factor, and the Rydberg constant is proportional to the fine structure squared. So some sort of numerical factor and some sort of other factor which depends on alpha. And that can depend very strongly on alpha or not at all. So for aluminum plus, the sensitivity is exactly 2, and this 2 will cancel between different clocks. So generally, if we compare two of those atomic clocks with those optical transitions, you don't care about Rydberg constant, that always will cancel. You only care what the extra factor is. And the extra factor, it's the largest extra factor, as I said, it's 6. So for Mercury plus, that was 3, but that clock, no one dares to operate anymore. There was one fantastic experimentalist who was able to build it, but no, it's very, very difficult. So in the case of other transitions, it's possible to actually use hyperfine transitions. So for now, as I said, this depends only on alpha. Okay, why not? But we actually have a paper, we figured out how to make it actually, how to search for gluonic couplings and how to search for the quark masses. So this paper is not on the arXiv yet, but it's supposed to be on arXiv next week. And the one other effect which you can use, and this is, by the way, tells you how highly varying the field is. Any paper you essentially read right now is going to tell you that optical transitions you can only test for alpha. But there is another effect, because if fundamental constant changes, the radius of the proton is changing. And as the radius of the proton is changing, so is the radius of the nuclei is changing. And that actually affects things called isotope shifts. So there's an energy shift depending on how many neutrons you have in your system. And this actually allowed us to get actually coupling from optical atomic clocks, both to the QCD axion, because it's actually a similar effect, and actually also to the couplings to gluons and couplings to quark masses. And in this case, it's going to be first paper of this kind. So sometimes you may find new effects later. And also the first paper on dark matter searches with clocks was in 2015. So it's all very, very recent. So, but as you see, people have missed it. I mean, everyone thought that you're not sensitive to anything nuclei because it always cancels out. But it turns out to be it's not the case. Now, one other thing in principle you can do with atoms, you can look for those microwave transition. So for example, the clocks which are on GPS are based on cesium and rubidium. And they're very different. They actually use a ground state, and they use a splitting, the microwave splitting of about a few gigahertz as a clock. Unfortunately, these are not great clocks. So the optical clocks are much, much better. But in principle, this type of transitions, they're actually sensitive to more fundamental constants. And some of the very first actual limits come from them. Because frequency here depends again on Rydberg constant, but then it also depends on a thing called a G factor, and that actually has connection to the nuclei. And from that, you can actually get dependence on a quark masses to lambda QCD. Then it also depends on ME to MP ratio with a factor of 1, and also there is some sort of different other form factor. The only problem is that these clocks cannot be better than 10 to the minus 16. That's an absolute technical limit. And we are at that absolute technical limit at this point. So whatever we could do with this clock already been done. There is an alternative of this type of transition which becomes optical and highly charged ions, but that clock would be hard to build. But in principle, that's why you actually see limits on those things already from clocks. They all come from comparing to microwave transition. That's called microwave transition because this frequency lies in the microwave range. Now, the other thing which you can do are molecular clocks. Molecules are very, very hard to cool. So molecular clocks only still at the 10 to the minus 14-ish rate, much worse than this, but we have a hope to have high precision clocks. But we had that hope for the past 20 years. So hopefully now, maybe next few years it will happen. The reason why the clocks are sensitive to different fundamental constants, they're sensitive to ME to MP ratio. The reason being because molecules also have vibrational and rotational degrees of freedom. And if you compare electronic, rotational, and vibrational transitions to each other, then you will actually have dependence. So electronics does not depend on them. The rotational, vibrational depend as ME to MP, square root, and rotational is ME to MP. So comparing different types of transitions would actually make you dependent on some factor of ME to MP. There are also some accidentally large enhancements to ME to MP ratio in some of the molecular clocks. And the nuclear clock would depend on alpha and very strongly also to the quark masses to the lambda QCD. And when I say quark masses, this is generally assumed to be an average of light quarks, because that's what you get in your nuclei in atoms. So this is pretty much it so far. As I mentioned, there are some other new ideas of what you can do because you just don't have, your muons and atoms, so you constrain to those particular constants. But you already actually get couplings to the electrons, to the photons, to the gluons, and to the quarks. And you can constrain all of this. So if your dark matter couples to any of this, this is actually direct dissection experiments, which I'll show you how that actually work. Questions on this? So I did summarize all of this for you. So this, I'll actually post those slides. So if you're interested, you can actually take a look. And the other question is, how do we know how sensitive those things are to fundamental constants? Well, the energy levels all the energy levels in atoms are proportional to the square of alpha to a certain factor. And as I said, we can just simply compute it by changing alpha in the codes, rerunning the energy levels. So those are computed extremely well. But then when you compare this frequency of two clocks, your alpha variation test and all of the dark matter tests which come from it is then proportional to the difference between the enhancement factors, and this is just to make a dimensionless, between two clocks. So if your factor is 100, then if you measure the ratio of frequency to 18 significant figures, your dark matter search is then 10 to the minus 20. So essentially, it's just simply easier to measure large effects. And in this case, the sensitivities are computable for the atomic and molecular clocks. They're not computable for the nuclear clock, because it's a nuclear calculation. They actually been estimated and derived. Now we can make an experiment to actually determine that. Any questions? Okay, I didn't quite get to that. Okay, and then how clocks actually work. The one thing to note is that the line between atoms, atomic clocks, and atom interferometers is becoming a bit murky. Just because the atom interferometers, which are people now building as a prototype gravitational wave detector, and those actually the ones which were also sensitive to dark matter, use exactly the same system as clocks. For exactly the same reason. They actually need to be able to have a metastable one-photon transition. So all of them right now, atom interferometers, are then switching to strontium or terbium, and that's exactly the system which is used by clock. So there is also a technical difference. In atom interferometers, you can actually, for some reason, mostly you keep your atoms free, you don't trap them, because you need to kick them and make them move. In clocks, you absolutely must have them trapped. However, there are already first interferometers in a cavity which actually will use optical lattices for some precision measurements. So as I said, the line kind of becomes a bit blurry. But I'll show you how both works. So we have a two-level system in atoms. Let's say all atoms are generally in a ground state. Generally, almost always, actually, for all current clocks, this is a ground state. That's the lowest energy state of a system. Atoms don't have anywhere else to go. So the first thing which you do, you actually split the state to two states. For purposes of comparing to interferometers, you can think about those things as beam splitters. In our case, your beam splitter is a laser, and I'll show you why that actually works. So the first thing you should do, you actually split this to superposition of 0 and 2 in exactly the same ratios, half and half. And this is a quantum formation technique. People know how to do it, and again, I'll show you how. And then you wait. What happens when you wait? Well, superposition starts to evolve because there are a Hamiltonian which governs evolution of both of those states. And because now this is in state, like for example, if you have your strontium 5s squared, and this is 5p, they evolve differently. For the obvious reasons, those are different electronic states, but mostly the biggest problem, essentially, and the whole goal of our point, we are comparing what's the frequency of the laser relative to the frequency of the atoms. If the laser is perfectly on resonance, it will make this perfect superposition. However, the whole point of the clock is a tuning instrument. Your atom frequency is perfect. It's given to you by nature. So what you do, you tune the laser to the frequency of the clock. And when it's perfect, then you make measurements. So when your laser actually starts straying off the resonant, the superposition which it creates, it's not perfect. Also, it's not perfect because when it starts evolving, there are different levels affected by noise differently. So for example, this is more affected by electric field than this one. Also, this is more affected just by temperature. Those are such precise clocks, they're actually affected by the fact that your temperature in the room is 300 Kelvin and it's still 300 Kelvin in your trap. They're actually affected by simply blackbody radiation. They essentially you can make temperature measurements with those things. In fact, the blackbody radiation already contributes at 10 to the minus 15 level, and we are at 10 to the minus 18. So what happens when you wait? Well, the frequency starts to evolve. So you have, since the total phase can always be taken out, we don't care about it, but there is some evolution of one state relative to the other. And in principle, you can think about at this point, you can measure the atoms, but the procedure which gives you the best experimental result to see just how much you are now off comparison to your laser and how much you have to steer your laser back to atoms, you actually do another beam splitter. So you again split the state 1 and split the state 2. So you do exactly the same one more time, only generally you actually use somewhat different types of laser pulse for this case. So, and for all the purposes, and let's not worry about normalization, you end up with 1 minus, don't worry about the minus, and this is maybe some different phase in this case. and all it can be, and then, no, actually the same, plus 1 goes here, and then that's for unitarity. You actually, if you do the calculation, you'll see you have minus sign there. So as you see, you now get a sort of position, oh, I'm sorry, 1 minus this. So both of those are now 1. I'm sorry, 1 plus this, both are now 2. So you see the 1 now splits to 1 and 2 goes now back to 1 and 2. And then you make measurement. You measure how many of your atoms are in state 1, and you measure how many of your atoms are in state 2. And this information gives you information about just how much of your laser was from proper atomic frequency, and you use it to correct the laser frequency and steer it back. And then you actually wait, and then you do another measurement. You can actually do continuous measurements, which means you always know what the frequency of the laser was. So what you're actually measuring, it's a ratio frequency of this clock to the other clock. One of the critical points is how long the wait time can be. If the laser goes out of frequency by pi/2, this is not correctable. There are tricks to avoid that, but the point is your wait time is limited by the lifetime of the atoms and by the stability of your laser. And now, what is specifically do you actually do to actually make the split? As I said, I called it beam splitter because for the analogy of atom interferometer, but all it is, it's a laser pulse of specific duration. How many have actually taken time-dependent perturbation theory somewhere at some point? Raise your hand. It's some quantum mechanics course. Okay, a few. So if you ever had worked out atom-laser interaction, the time-dependent perturbation, so what happens when you actually have your atom 1 and 2 and you're shining a laser to it? So all it is, it's actually your atomic wave function. It's some superposition of those two states. You turn on the laser, you write the Hamiltonian. You write the Hamiltonian of your atom-laser interaction, and you say if your laser is on, what you actually end up with, it's this. That your C obviously can be from 0 to 1. So this can be either all 1, all 2, or the superposition of the above. So the C varies from 0 to 1. And essentially it varies like this. So the result of time-dependent perturbation theory is that if you have the laser on, that your state 0 eventually will become state 1, then it goes back to 0, back to 1. And that actually happens, the 50-50 superposition, when it's actually 1/2, will happen after your laser is on for the pi/2 time. This is called a pi. This is 2 pi. This is 3 pi/2. So as you see, turning a laser on for the duration which corresponds to pi/2 will make a superposition of your two states. So all it is, this beam splitter, is a pi/2 laser pulse. And pi/2 refers to the duration. And again, all you need to do to actually make a superposition, again, that's another pi/2 pulse. You would think that they actually make them the same, but I talked to experimentalists, and for technical reason, to absolutely maximize the result in a phase, to maximize the phase measurement, to maximize how much you actually can get out of a single measurement, the first axial rotation goes around the x-axis of the Bloch sphere, is another one over y. Again, that's for technical reason. There are different schemes when you actually don't do this. You will simply excite all zeros to all ones and wait, and then brings them back. That's called the Rabi method, but generally everyone using this Ramsey scheme. For dark matter searches, you have to use this Ramsey scheme because during the wait time, that's when you accumulate the dark matter signal. So I hope that answers your questions or not. Yes?
You said the way you actually measure it is by counting atoms.
You're literally counting atoms. Or, okay, if you have a lot of atoms, then you count atoms. If you have one atom, you just get one bit of information. Was it in 0 or was it in 1? That's called quantum projection noise. So you count atoms, or essentially you're measuring how many atoms are in state 1 and how many atoms are in state 2. So if you have 1,000 atoms, then this is literally the number measurement. If you have one atom, it's a measurement what state the atom is in.
But then wouldn't the precision of the phases depend on how many atoms?
Absolutely, and I will show you the formula. Yes, that's why it's unadvisable to use one. They just didn't have another choice. Ions, for many reasons, actually, you can actually get away with. It's a simpler clock. You can actually get away with one ion. So accuracy is actually the same for atom and ion clocks. It's stability which is it's affected. So it takes longer time to reach your ultimate clock accuracy with one ion. But you see, actually, you raise a very interesting point. So if you have one atom, you can only get one bit of information out of this measurement. That's actually pretty much what quantum projection noise is. There's simply no way of getting any more information. If you have n atoms, then you can get square root of n more information. If you entangle your atoms, you can get n more information if you have n entangled systems. But again, this brings us down that we are actually in many measurements in tabletop experiments, they're that good that we actually at the quantum projection noise limit. So the fact that we only can get one bit of information from this measurement, if you have a single ion, it's the one which is limiting a lot of experiments now. So in fact, I'm in an institute which specific goal to actually go beyond the standard quantum limit. Because in quantum mechanics, you're allowed to. In this case, you have introduced some degree of entanglement on your system. So the absolute limit, which quantum mechanics tell you, is not the standard quantum limit, it's the Heisenberg limit. When your system is completely entangled, there's nothing else you can do with quantum mechanics. That's an absolute ultimate limit, and we have not reached it for any measurements whatsoever. There's been only 2 successful experiments for precision measurements where this squeezing or this measurement beyond the standard quantum limit was successfully used. Surprisingly, the first one is not tabletop, it's LIGO. LIGO actually measures beyond the quantum limit at this point. They injected what's called a squeezed vacuum in their system in order to actually, that's what this, one of the most recent advances is, which went from run 1 and run 2, they went to the squeezed vacuum state. And the second one is haystack, it's an axion search. I will actually show you how it works today. But it's very difficult, and I think within 5 years, we'll see more and more of this. So because think about it, that means you control every other noise perfectly. So every other noise is below the standard quantum limit control. And in part, that's why we're here. That's why those experiments are so very good. So I wanted to ask back, so you had a question on the operation. Is that clear, or is there still questions? Okay, anyone else? So this is kind of the most straightforward way to operate a clock. For some reasons, occasionally, especially for the dark matter searches, you're also introducing pi pulses in between during the wait time. Why would you do that? You will do that if your dark matter oscillates faster than the wait time. Because you see, you're going to have a fast oscillating signal during the wait time, and meaning you're wasting your wait time. So one way it's reducing the wait time, but then you're reducing stability of the clock. So if you actually apply those pi pulses, it's like you apply many, many mirrors in between. It actually allows you to accumulate the signal which oscillates faster than your measurement time. And that's one of the quantum algorithms which we actually have explored recently. And this is called dynamic decoupling, or some other people called it quantum lock amplifier. So there are many interesting tricks which you can do actually with this. Okay, so how specifically do you use actually clocks for dark matter searches? So what is your procedure in your experiment? First, remember we are always comparing 2 clocks. There is actually no way of making an absolute measurement at 10 to the minus 18 level, so we are not measuring absolute frequency to 18 significant figures right now. In fact, this is not possible. Why is it not possible? Well, because our 1 second is defined by microwave clock. And microwave clock is only accurate 10 to the minus 16. So until we redefine what second means, we can't really do absolute measurements to 10 to the minus 18 or 20. It will be redefined within maybe 10 years at this point. Because now, I mean, those clocks, like there are many clocks in the world which are 2 orders of magnitude better than your definition of a second. So, but it's perfectly easy and possible to just have 2 clocks, preferably not too far away for now, and then you actually compare them and measure the frequency ratio. So I will tell you a little bit more how it's done, but for now, we are just going to assume that during this procedure, and we're actually running 2 clocks in exactly the same way, and our observable is the clock frequency 1 divided by the clock frequency 2. For many experimental reasons, it's a ratio and not a difference. It's much easier to measure ratio than the difference. And that's all we care about. So what we do, we actually make measurements during some relatively long time. How long time depends on the nature of your experiment and whether you're in Metrology Institute who can do it forever, your grant, your grant lengths, or how often your students can be in a lab. And, you do not have to make the measurements all the time. You just get better if you measure it all the time. In some of the measurements, people have actually done the measurements every 2 seconds or for almost 6 months, and at that point, the system ran relatively automatically. So people had to check on it every once in a while. And I've looked at the data, we actually analyzed this data, and here, like, there's 3 weeks, there are no data. Like, why? Well, we've done something to the clock and then had to sort it out how to fix it back. So it's okay if you're missing a couple of this analysis, if you're actually missing a few weeks out of a few months, or you can just do a measurement campaign for, say, 10 days or so. So remember, 10 to the 6 seconds, it's 11 days. Now, it's in principle best to measure as long as possible, because eventually you'll be many coherence volume or dark matter. But then you actually, eventually you start losing accuracy because your dark matter is no longer coherent. Okay, so now you make this measurement. Let's say your wait time is 1 second. And let's say you have no dead time. So what is a dead time? The dead time is the fact that if you have an optical lattice, the thing and your atoms need to be cooled down, because anytime you make a measurement, what number of atoms you get, you're actually scattering light of your atoms. It makes them hotter. So generally, you need to repeat the cooling procedure in between your measurements. So it means that generally you're wasting about at least 0.5% of the time. So, half of the time. So generally, in most clocks, the wait time is at least no more than half of your measurement time. The more complicated your lattice, the longer the wait time to make sure it's all cold and ready for the next measurement. There is a very easy way around it. Okay, just operate 2 clocks. So the laser either talks to clock A or to clock B, while clock A talks to the laser, clock B is being cooled, so you can run it with 0 dead time. It's an obvious technological complication, but let's put it this way. Most of clocks are in metrology labs. That's all those people do. They build clocks. So usually by now, a metrology lab has a few clocks of the same type because they're built differently. Because they constantly need to improve clocks, so they're building more and more of them. For many reasons, they build 2 of the same kind. So in principle, you don't even need to build 2 separate clocks. All you need to do is just to make 2 atomic clouds and put them on a lattice, and then you can make those measurements. So it could be the same clock, the same laser, only you have 2 actually atomic samples in the same clock. That's been demonstrated too. So for our purposes, dead time is a technological issue which we know how to actually fix. So let's say there's no dead time and you make measurements every second. And every second you actually record the frequency ratio of 2 clocks. Now, for now, let's say we only have 1 dark matter oscillation or less than 1 dark matter oscillation per time. But in order to do Fourier transform, you need to get at least 1 dark matter oscillation during your entire measurement campaign. It's best if you actually have at least 4 to 5 oscillations to get the frequency. Then you get all your time sequence and you just do Fourier transform, discrete Fourier transform from time domain to frequency domain, and your detection signal would be peak with monochromatic frequency, which looks a bit like this. It's a little bit asymmetric just because, remember, the dark matter has dispersion and we are moving actually and we get dark matter window now here. So this is literally direct detection signal, and you actually can get dark matter mass because the Compton frequency of dark matter, which you will see, is actually directly dependent on dark matter mass. You will not, unfortunately, get dark matter coupling. So, well, you'll know which coupling you have, but not the strengths of the coupling quite. So in this case, that's your signal, but just because you don't see the signal, you can actually plot, exclusion plot mass versus coupling. So this is perfectly fine. So you will not get how many of these particles you get in the universe. Okay, so and you can plot the coupling. You can plot the coupling versus mass exclusions. That's perfectly fine if you're not seeing anything. So, okay, now, okay, let me correct. You do get the coupling. You do not get the density. So because your detection is not connected to production, you can't quite tell how many of those particles you get in your galaxy. With axions, if you actually also count solar axions, you can eventually, but you have to see solar axions. Okay, one issue, what is your dark matter oscillates faster? Well, then you can actually use either improve stability and just make measurements time shorter, and you use dynamic decoupling, meaning you just start applying those pi pulses. Unfortunately, there is a limit of how many of those pi pulses you can actually apply before you actually start introducing a lot of errors. And that what actually limits your dark matter sensitivity to about 10 to the minus 12, 10 to the minus 13 EV, and then all the way down to 10 to the minus 22. But it's very hard with this procedure to actually measure the scalar dark matter with a frequency which corresponds to masses larger than 10 to the minus 12 or 13. However, there are plenty of other experiments which will do that for you. So any questions on the detection? So it's a broadband detector with a range of maybe 10 to the minus 22 to about 10 to the minus 13. Now, if you actually see the signal, you can make it narrow band. So if you see the signal, you can actually apply the pi pulses which corresponds exactly to the dark matter frequency. This actually allows you to improve the signal significantly. So if you see anything, you can actually do significant improvement just in this range and get stronger signal. But for that, you need to know what dark matter mass is. Okay, I'm going to stop here, and if you have questions, and come chat with me. Okay. So here is how much the precision of clocks improved. So those clocks are microwave clocks. Okay, shh. Have a question? I'm happy to answer. Question? Okay. But look, questions are extremely welcome. So ask question to me. This blue line, it's improvement of microwave clocks. So microwave clocks, as I said, those are a few hertz. So the standard of second is done by cesium. And as you see, that got to minus 16 and pretty much stuck there. There is no way of improving those clocks, make them any better for many reasons. And this is an ultimate technical limit. Their frequency is just not high enough to make it any better. Also, there is just, as I said, there are both technical and practical reasons why that can't be improved. So eventually, cesium will have to no longer be a definition of a second because these are those optical clocks. As you see, there's kind of sort of a Moore's law of optical clocks. They almost improve like a factor of 10 in 5 to 10 years, a factor of 10 in about 5 to 10 years. So by the way, at 10 to the minus 18, where we're right now is slightly better. This clock will not lose 1 second already in 30 billion years. So there are already new prototypes which already have stability to 10 to the minus 19 at this point. So we'll be in 5 years, we'll be right here. How far the rabbit hole goes depends on the optimism of experimentalists you talk to. At the point of 10 to the minus 18, if you have one clock on this table and another clock of this table, it already can tell it can tell the difference. It can measure the height difference of 1 centimeter. Right now, there is already 2 clocks which can measure height differences between actually atoms in a lattice of a millimeter scale. So you can measure gravitational redshift at a millimeter scale with current clocks. So by the way, if you're wondering how then you start comparing clocks when there's such an environmental difference, in principle, when I say clocks, they don't have to be physical clocks. They just have to be 2 different transitions. We have ions and atoms which have more than 1 clock transition. So you literally can have an ion and just run a comparison with a single ion or with a few ions. But you first probe 1 transition and then another transition, and you measure the frequency of them. So this has been done. This is also possible. So it don't need to be 2 different physical devices, for example. So as you see, the precision have been actually extraordinary. So as I've mentioned, so what we actually measure, and there have been a lot of interesting questions about it. So clock, for the most part, it's a tuning instrument. So you attach to your musical instrument the standard of frequency, and that's your atoms. And then you tune your laser to make sure that you're exactly on resonance with atoms. Because think about, okay, that's your excitation curve for the transition. There is this perfect frequency of atoms. If your laser is off, line width's off, so if your frequency of the laser is actually different from the width of the transition, if it's right here, what happens if you try to do that, if you use this laser beam splitter? Absolutely nothing. Your atoms all stay in one. You will not make the superposition. So then you tweak your laser, and then you do it again. And now you actually, get some of them on 2, and eventually you essentially get a perfect split. So what you're actually measuring, it's a phase difference or a frequency difference between your laser and your atoms. So your atoms, it's a perfect standard. They're always the same. Besides, the environmental effects and stuff which just happens, besides the systematics, they're perfect. The laser, however, is not. So generally, the laser is worse frequency standards than an atom. So all you do, you use your atoms in this procedure to actually get the laser exactly on resonance with frequency, and then you can make this measurement of frequency ratios. So as you see, it's a bit more complicated than I said, but the whole purpose that you're actually using this number of atoms, because that's what you're actually measuring, to measure the frequency between laser and an atom. When it's perfect, as small as possible, which this clock can do, then when you actually measure it with a different thing called a frequency comp. And you're in this point not measuring absolute frequency, you're measuring the frequency ratios. So this is how the process looks like. So you have this interrogation laser, you have a feedback control, and this is your how the atomic transition looks like. So as you see, there are all those many, many data points. It's those different frequency of the lasers trying to make this transition. And you have this wait times, you measure population in different levels, and then there's an automatic servo loop which changes the frequency of the laser to tune it exactly on resonance. And that is a device called the optical frequency comp, which is another laser, which actually allows you to compare a frequency coming from 2 different clocks. There was a good question, what is you only have 1 atom? Well, then you only find out if it's in state 1 or 2. You don't get that much information about it. Clearly, in some cases, I've been told somehow experimentalists can actually steer it from 1 measurement, but mostly they just make several measurements and you have statistically significant when it's like more 1 or more 2s. And all of that is actually technologically more complicated than this, but this is a basic idea of what you do. It's kind of a bit weird thing. So what you actually measure is a population, and then you literally measure the frequency ratio with this other lasers. So this other lasers essentially allows you to connect electronic counters to the optical frequencies, because there's no electronic counter which can tell you what the frequency is. It has to be done with another laser. In fact, this is the reason why this curve starts right here. There was actually invention of this frequency comp was people got Nobel Prize in 2000, and it was almost right after that was actually invented. Before that, you couldn't do optical clocks because you can't measure optical frequencies. Now, when I say you compare two clocks, what you do, you're operating a clock, say Mercury plus, and then you're operating the clock with aluminum plus. Don't worry about this beryllium plus thing. It's this whole quantum logic clock. You can't directly control this ion. You actually use another ion to control it. And now, and those are those ultra-stable cavities which are part of lasers. That's why I said you can actually measure the frequency in a cavity to the frequency of the atoms. And then they all connected through fiber links to the same other laser called the frequency comp. And that actually allows you to get this frequency 1 divided by frequency 2. Again, for technical reasons, it's a ratio, not the difference. So you don't know what actual nu1 or nu2 is. You only know the ratio out of this procedure. In order to be able to actually measure the nu1, one of those things have to be connected. You have to connect this to the cesium clock. But again, then you're limited by the 16 significant figures anyway. So questions? And as you see, in this, one of those clocks have sensitivity of minus 2.9, and another one essentially not sensitive. The aluminum is very light, so your sensitivity total is about 3. Okay. Now, we've mentioned which atoms are used for clocks. So either you actually have a neutral atom. This is actually an ion, but it has a very similar type of transition, or you literally use a single ion. And of course, you may ask, well, but wouldn't the single ion be so much worse? Well, for the longest time, people had significant problems with controlling neutral atoms comparing to ions. So now, actually, you have about the same uncertainty for both. And I've used the word uncertainty and I used the word stability. So there are two completely different parameters which describes how good the clock is. And in terms of dark matter searches, we really need to know about both. Okay, so let's say you throw darts. And well, I mean, some darts are on center, some darts are off center. And what you do, you average, right? So the stability is usually increases as a function of averaging time. This is how good we can measure a quantity. The second thing is uncertainty. Think about this is statistics and this is systematics. You can actually get all the darts perfectly in the same spot. It's just not the right spot. And you measure those two things different ways. Here you literally have to think about all physical effects which can actually make the clock frequency not what it would be in a perfect vacuum with nothing around it. So the temperature will do it, the electromagnetic fields will do it. For ions, the trap itself would actually make ion jitter. You have Doppler shifts in that case if it jitters. The errors in the server, the errors in your laser, the errors from the fact that atoms, while they're trapped, most of them are in one-dimensional traps. There are collisions between atoms. There are collisional shifts. There are ways to suppress all of that, but experimentalists think about everything. You literally have to think about even stuff whether continents drift, and whether there are what things called solid tides, of what's in gravitational environment about you. But generally, those things are very well understood. The things which generally is the worst understood, that's the effect of temperature, the black body radiation, and in case of ions, the effect of its own trap. It's just very hard to fix. So the way people assess those things are this way. First, clock stability. If you are at the quantum projection noise limit, your clock stability is affected by the frequency of the clock. This is why optical frequency is so much better than the microwave frequency. Because remember, for optical frequency, this is 10 to the 10. For the microwave, that's 10 to the 14 to 15. So going from microwave transitions to those optical transitions automatically improves stability by 5 orders of magnitude, just because you use different transition in atoms. That's why, pretty much people stopped, progressing much with microwaves, because there is just an absolute limit of stability here. You just can't make it any better. It takes too long to get to your ultimate uncertainty. Then the number of atoms, yes, for ions, n is 1. For neutral atoms, it's about 1,000, so it's automatically better. And it is a problem, but there is ways to mediate it, and people are already on the way of actually making multi-ion clocks. It's really a technical issue, so why they're operating with a single ion. And also, single ion traps are much, much easier. It's just a radio frequency trap. You can trap a single ion with like a piece of wire, pretty much. With the multi-ion traps, I mean, that's more complicated. There's a radio frequency and quadruple trap. However, it's a control of several ions in the trap, which generally just the literally jittering of ions, which creates too many errors for people bother with it until we actually reach right now. Now, and this is interesting. This is a duration of the single measurement cycle. That is your wait time. So this is why people want to wait as long as possible. Because if your wait time is a second, or if the wait time is 100 seconds, you have a factor of 10 improvement in stability. Unfortunately, for 100 seconds, if you're looking at the dark matter, which is a 10 to the minus 13, you have a lot of dark matter wavelengths already happening during this wait time. So you see it's a bit of a counterindicative to actually searching for dark matter to have a longer probe times. So in this case, you can increase the number of atoms and shorten the probe time to be sensitive to heavier dark matter. And this is also how long you measure. So the longer you measure, the better you get until you hit the uncertainty. If your uncertainty 10 to the minus 18, it doesn't matter how long you measure, you still never get better than this. What's important here is how quickly you can get to 10 to the minus 18, to your ultimate uncertainty. And in ions, it will take longer, it could take hours. In neutral atoms right now, you can actually get to the ultimate uncertainty in 4 seconds, very, very quickly. For those microwave clocks, it kind of takes forever. So this is why it's important that we actually deal with both. And just to summarize, this is how it looks like. This is uncertainty budget of the clock. This, remember, how off-center your darts are. And as you see, there are many things. The Stark effect, the static blackbody shift, a thermal effect, Stark shift, its effect of electric fields, Zeeman shift, effect of magnetic fields, density of atoms, meaning collision, collisions with background gas, which has nothing to do with atoms. This is just a server between laser and atoms. And then there are just technological, some of the technicals and some is physics. And then you add everything in your quadrature, and that's your ultimate uncertainty of the clock. Remember, that's your best estimate how good your clock are. To eventually prove it, you need to compare it to a different clock and see whether you actually match the uncertainties. For the stability, as you see, you keep measuring, and eventually you get to this point. And here, that actually at 10 to the minus 16 stability per square root tau, and that's how long you measure, you actually, there, you get at 10 to the 3. The best measurements, you actually get it now down, like at this point, you're already like right here. And that is the absolutely best measurement. Stability, as you see, this is actually, you get in at 10 to the minus 18, in already, that's 9 seconds, but I know that group already got to 4 seconds. And here, they can just demonstrating stability because they can actually compare atoms in the same clock. You can actually get fantastic stability. So this is stability with neutral atoms. This is essentially a solved problem. With trapped ions, well, they need more ions. This is a gravity measurement. They actually tell the difference in position of atoms in this part and this part. So they actually measure the redshift at a millimeter scale. There are 2 teams in the world which done it recently. And you see that's 2022, that's new. So first, I wanted to ask a question. So are there any questions either on this clock projection noise limit or on this identification of how good the clock is? Yes?
On the duration of the measurement?
Yes.
So, I mean, you have this phase delta, but
Right.
if it goes above 2 pi, then you're back to where you started.
In fact, if the laser phase go over the pi over 2, this is not fixable.
Right. So So then doesn't that limit how long you measure, or how long you can wait?
Yes, it limits how long. Pretty much, you're exactly right. Right now, we are limited by how good the laser is.
Okay.
There are tricks, however, because as I said, there are only two really fantastic lasers in the world which you can actually wait for several seconds. Because the problem becomes very technical. In the laser, there is a cavity. And how good the laser is pretty much determines how good the cavity is. Do you know what actually limits the accuracy now? It's the Brownian motions of atoms in the mirror of the cavity. It's literally the thermal jittering of atoms. It's that good. So the only way right now to fix it is really physically cool your cavity. So right now those cavities are cryogenic, they're at 4 Kelvin. So at cryogenic cavities, they think they eventually, I think they're at 70 Kelvin now, with 4 Kelvin, they think they can get to 100 seconds eventually. But also this is material science, how to make perfect mirrors. It's pretty much like the LIGO, how to make perfect mirrors. And that's a physical, it's about like that big thing. So.
How long does it take to get to 2 pi?
Oh, that depends on a particular clock. So as I said, with these lasers, several seconds to get it's a power 2 actually. So power 2 is not correctable phase. But there are so many tricks. So this is when you have one laser and one clock. If you have multiple clocks, you can use tricks. You can actually do differential measurements. So, and you can, if you, for example, one clock has a perfect laser, another clock not so good laser, it's okay. You can actually measure one clock and then fix the laser phase for the other clock before you make a full measurement. So there's lots of, and that's actually what quantum information people tell us, how to use various quantum algorithms. It's called so experimentalists have a lot of tricks how to fix a lot of those problems. So you can actually, comparison like this, you can do with very bad laser because as long as you're not making any absolute measurements, you're just comparing clocks, you compare atoms in the same clock, you're shining the same laser, you cancel all the laser noise. So you can measure the redshift with a very bad laser. It's measuring this clock to the other clock, what you need a good laser for. But again, only one of them have to be good. So measure, in essentially, all of that just leads to the complication of your device. But people have been very inventive. And you see, field progressed extremely rapidly. I remember 10 years ago, we were talking about 10 to the minus 18 as kind of like the ultimate result of this. And now people talk about 10 minus 20 when we're here. So this progressed much faster than I would have ever thought it would be possible. Other questions? Okay. So what's next and what is the result? By the way, that's how the clock looks like. If you've ever been to the AMO lab, they kind of all look like this. There is a lot of optical instrument. Yesterday, I was in the Guglielmo Stina's lab, who is atom interferometry expert, actually, like really one of the best atom interferometry group in Europe and in the world. And they actually showed me, like literally, you can actually look at, so inside this chamber somewhere, there are those atoms. In the turn of the light, and I could actually see the atomic cloud in blue because they had the blue light and the light was scattering of atoms. It's like there is suspended blue cloud. Can actually literally see it. And mostly it's somewhere inside the vacuum chamber. I'm not sure why the air is transparent and you can actually look at it. So, and it's, usually experimentalists don't particularly care how large this thing is. Usually the frequency comes on some other table and some other laser is another table. But there is much more compact versions of this as well. By the way, if you're wondering how the quantum computers with atoms looked 5 years ago, they looked about the same way. Now they all on a chip and miniaturized. So you can miniaturize those devices if you need to. So lasers are harder to miniaturize. We kind of stuff ultra-stable cavity. It has to be a specific size. Also, they consume power. And all of that is relevant because you want those clocks to be portable. Now, in terms of the clock comparison, what limits us? Right now, all of those clock comparisons are between the clocks which are nearby or in the same labs. Like the same building was okay, nearby okay, because we can link the fiber optics. There have been comparisons over free space. Right now, we cannot compare clocks on different continents. In Europe, people have done fantastic fiber comparisons over. Any problem? We actually had, in Europe, there's been comparison between France and Germany. So there's over 1,000 kilometers comparisons. You literally need to deal with commercial systems because you cannot directly use commercial fibers. You need to actually make some, allow you to make changes to the fiber. It's very expensive. So the dedicated fiber cost in the US for the 30 kilometer of the fiber, it's 30,000 per year to lease it. So that's why we need clocks in space. Yes?
This picture
Yes?
is not broadcasted on Zoom.
Oh, why? Is that better? What?
No, I don't know. I was checking.
Weird. Okay.
I have this impression. So this comes from your computer, right?
Yes.
Okay, it must be right then, because nobody complained.
Okay. Okay, to summarize, those devices are, as you see, tabletop. They already have prototypes which are about kind of meter by 2 meters. So people already put them in a van. They already have portable versions of this. So there are several portable versions in the world. I'll show you how they look like. Usually there are several of them in the same place because mostly those efforts have been in metrology labs. The startup cost to build something like this is a faculty starts to build like this. It's like equipment plus postdocs, grad students. It's $1 million to $2 million startup for those. So it's expensive, but not very expensive. And it's become cheaper now because already a lot of those parts are available commercially because a lot of grad students and postdocs and faculty went and organized startup companies which make some of the parts of this. So usually, there are several clocks, meaning you can run those experiments naturally. And the other thing, metrology people have to compare clocks. If we ever do redefinition of a second, there is a protocol document of what have to happen. Clock comparisons of different types are actually a part of the metrology protocol to redefine the second. So you get dark matter search for free. The data already exists. And actually, they have to report to the international time scale. For that, you have to measure frequently. So in principle, the dark matter search is initially a very simple byproduct of normal metrology operation measurements. To actually do it as good as possible, you need to do some of the specific protocols and also you need to build different clocks. Because those clocks were built from systems which were not designed for this, they are not very sensitive. So the sensitivity factor at most is 6. So now there's a new set of experiments which are building different clocks which have much, much higher sensitivity, and I'll show you the projections. But like, isn't it nice your dark matter detector is built for you? And in fact, those groups, if you have an idea, you can just contact the group and they will collaborate with you to analyze their data in terms of whatever your dark matter scenario is. Like in fact, when they had this new idea about oscillating radius, we just emailed a group in PTB with whom we already collaborated, and we are writing a paper together, not just a theory paper, but already using actual experimental data. So people are very, very friendly in the community. And despite the fact that they're actually in Metrology Institute, somehow they are all happy to search for dark matter. And eventually they'll be sent to space. And just to put things in perspective, there is many other reasons why people build clock and why they want high precision clocks. So first, the very long baseline interferometry. Who've seen this beautiful picture of the black hole? So eventually, to improve this, you need to have those interferometers in space, and then you need much better clocks to actually connect them. Also, this interferometer, they're already asking whether they actually use quantum memories, because optical signals, the storage of those optical signals, there are a lot of problems actually of how that actually works, and that's interesting. I have no idea where this is going to go. Then, as I've mentioned, those clocks are sensitive already to the centimeter in height, and between now they've been prototypes to the millimeter. Geodesy people eagerly await to be able to put those clocks in different places in Europe and sort it out the difference in European measurements. Because each country in Europe has its own height standard. It's a tidal gauge somewhere. And despite the fact that you can actually make classical measurements to fairly high precision, no country is going to say that my is worse than yours. So there's about half a meter differences between different European country measurements in terms of actually really what the sea level is in this case. And this actually affect the climate studies, it affects various geodesy studies, and literally the only way to absolutely fix this is actually put transportable clocks in this point. Clocks can tell you exactly what the difference is. And also you can use atomic gravimeters to look for the difference in gravitational potential, to the point that Japan actually has effort in to see whether actually the clocks can actually predict earthquakes and predict volcano eruptions. The current clock would see magma chamber fill in with about kilometer per kilometer empty or full space. You can actually tell the difference. Honestly, atomic gravimeters are probably best for this, actually. So atomic gravimeters right now can actually tell whether there is a full track or an empty track to that point. So the gravity measurements with atoms have been incredible. So those are kind of complementary atomic interferometry devices. Then eventually the seconds be redefined. Also the clock is essentially a quantum simulator, and all of those has nothing to do with fundamental physics. So as you see, there is many other applications. And then of course, search for fundamental physics. Clocks would be eventually as precise to be able to detect gravitational waves in space. You need about 10 to the minus 20 stability for this. And what? Well, the projection was for the strain was 10 to the minus 20, but with atom interferometers, you can you still need to push a few parameters. Now, the other grid, so that's for this decihertz frequency range, but for the frequency range, which is actually let's say, smaller than LIGA than LISA, so to the left of LISA. The only proposal which exists is putting clocks on asteroids and measuring actually the distance between the asteroids. So use asteroids as a test masses. And right now for that, actually 10 to the minus 18 is enough. So there, the more uncertainty is we don't know much about asteroids. They think the clocks can actually measure the position of the asteroids which are separated by like astronomical unit to a micron. 10 to the minus 18 gets you a micron. So with that, people can think you can detect gravitational waves as well. I will show a little bit on gravitational waves in the end. So for the fundamental physics, we talk dark matter searches and variation of fundamental constants because you get that automatically for free. The clocks actually have been used to search for violation of Lorentz invariance. The best limit on this for electrons come from clocks. Actually, we've been part of that measurement. Test of position invariance, and I mentioned gravitational wave detector. Position invariance is kind of simple. The 3% is centricity of the Earth's orbit. The sun is 3% closer to Earth in June than in July, than in January, or backwards. And you can actually use it to test position invariance. Questions? So efforts to improve. That's the current limits. And I will show the full limits. This is actually one of the latest clock limits. That's a dark matter photon coupling, DE. So this is, remember, coupling to F menu. And this is a dark matter candidate mass. And as you see, they do go all the way down 10 to the minus 20. These are equivalence principle tests. They're old experiments which actually were kind of looking for drifts. There's a new experiment, that's a projection for that experiment, but I'll show you a projection for other experiments. So that's kind of how this parameter plots for dark matter look like for clocks. So you also can put one for the DME, for D gamma, D gluon, and for the quark masses, but I'm just going to show the DE for one. I will show, so this is just for most recent clocks. I'll actually show you the combined one as well. Bless you. So, but the reason why they actually sloped, because eventually you lose sensitivity because you will just run out of the dark matter oscillation during the probe time. So 10 to the minus 15, it's about 1 second probe time, is like right here. And we already have ideas how to do better at 10 to the minus 13 or so, but eventually 10 to the minus 12 would be a limit. So how to improve? And when we say improve, we're not talking about factor of 2. We want to improve by many orders of magnitude, and we know how to do it. So how do you improve clock? Well, you can just improve current clocks. So the first measure beyond the quantum limit. So when you do those rotations, measure phase, usually your kind of error looks like a blob. It's possible to actually it's actually squeeze the noise. So you squeeze, so if you don't care about the phase in this direction, but only care in this one, there are procedures for actually how you can improve the sensitivity in one direction, and as uncertainty principle, of course, makes it worse in other direction. As long as you don't care about the other direction, it's perfectly fine. So there are actually ways to improve measurements of these phases. Essentially what you do, you pretty much, to some level, entangle atoms in your sample. That's what it does. So why does it work? As a very ultimately, why does it work is what? All good? So remember, our Allen deviation was proportional, to the 1 square root of n. This is your standard quantum limit. If you entangle your system, what does it mean entangle? Let's say you have, instead of this, your wave function is 1 plus 2. In principle, you can create this state, because then you just have, you multiply by 1,000 atoms, and they all work together, and that's the square root of n is 1,000, you feed it here. So that's how you do things. You just have 1,000 wave functions which are all the same. However, you can build this state. 1, 1, 1, 1, 1, many, many, many ones, all in the same wave function, plus all the 2's in the same wave function. Quantum computing experts can actually do superposition with like more than a dozen of them. Essentially, that's what squeezing does. Squeezing doesn't perfectly make this entangled state, but it makes it more entangled than this. So this is what entanglement means. So this is a fully entangled state. We are not doing this for squeezing because this is a different techniques. What you do, you make the 1,000 atoms slightly more correlated than just the product of the wave functions. So that's essentially what you do. You just make more connections to the point these wave functions are no longer completely unrelated to each other. There are different technical ways you can do that. The absolute limit is when you do this. If you do this, and you can keep this perfectly, you can do it for 1,000 atoms right now. But you can do it for less than 100, but more than 10. And eventually, that's what quantum information people do. They would like to be able to create those superpositions perfectly. For now, these states are fairly fragile. A lot of things can destroy them. But nevertheless, technology much improves. With ions, they would be able to eventually maybe do 10 or so, I think, in a reasonable space. They demonstrated it with 3 for the clocks. What does it give you? If your system is absolutely perfectly entangled, if you have 1,000 atoms, which is in this superposition, so all of them I evolve exactly the same way. So then this is not square root of n, this is n. This is a Heisenberg limit. You can't do any better than that by quantum mechanics. But you see there's a lot of difference between square root of n and n. So this spin squeezing is somewhere between the square root of n and between the n. Just how much in between, that depends on the level of squeezing, which is usually, for various reasons, calculated in dBs. Okay, don't worry about it. And that's right now where we're progressing this measurement beyond the quantum limit. And with clocks, we still don't. We have demonstrations, but not in a high precision clock yet. We will in a few years. That's actually one of the things for our institute. Then for ions, as I mentioned, we have ideas how to actually use 1,000 ions instead of 1. You have various designs for lattice clocks, and then also again entangled clocks will look like this. So all of that is going to happen. It's going to happen regardless of dark matter searches, because that is needed for many other applications and metrology. Also, clocks are needed by various agencies for various reasons. So there are so many practical applications. What we need for fundamental physics are different clocks. Like we need all of this. For different clocks, we can do all of those things as well. So it's important to study this. But what we want, first we want the clocks which are sensitive to different constants. And then we would like the highest possible sensitivity to fundamental constants. First, are there any questions about squeezing and the other stuff? I will go through it for the axioms, which is a very different kind of squeezing. But here, essentially, all you do, you pretty much make the system a little bit entangled. Not fully entangled, but more entangled than just simply product state. The system is not entangled if you can separate all the wave functions for individual atoms as a separate wave functions. Then it's completely unentangled. If it's entangled, means there is some correlation between them. Fully entangled, there's a complete correlation. If you measure this one atom in one, all of them are measured in one automatically. If it's in two, then all of them are in two. And this is as best that quantum mechanics allows you to do it. So this is absolute technical final limit on the clock stability. We are very, very far from it. In fact, I don't think anyone knows how to build superposition with 1,000 ions, 1,000 atoms. There are not even ideas how to do it, but eventually we will. Any questions on this? Yes?
How do you produce interval atoms?
Okay, how we produce atoms? Okay, first, apparently, I'm a theorist, but I've been told that there is essentially you can go online and buy quantity of an element. That's the first thing. Say you need strontium. You literally can order, and the vial come, and there is strontium in there. Some experimentalists during COVID bitterly complained that errors increased, and like you put it in and you shine your laser, not with clocks, but with that experiment, and nothing comes out. It's because they give you cesium and not strontium for whatever reason. So there is some strontium in the body, just not enough. So, but mainly you expect, and you can get a right isotope. You can say I need strontium 87. Or strontium 88. So when you need radioactive elements, it's a little bit different story. So, but there are national labs which produce them. But generally, you order an element, and then generally what you do, you heat it, and you make some atomic beam. So atoms start to just evaporate, and then you get them to your laser beam, and then you cool them. Like remember we discussed laser cooling. So now the atoms, atoms come from the oven like 450 Kelvin generally. And then you make them colder and colder and colder. And when they're cold enough, you actually use another laser to move them into the trap. You can shuttle ions actually by shining lasers in them, atoms. And you put them in a trap, and then you put your beams from optical lattices. If it's an ion, you actually put them in the ion trap. And I once spent a month in the ion group, which they spent the entire month looking for that ion. It just did not go into the trap. So it happens. But generally, you put them in a trap, and then you put your laser beam ons to make a lattice, and then they all just go into the states of the lattice, and that's the atoms are done. So that's kind of the general procedure. Does that answer it?
But how they entangle and the atoms?
How you entangle? Okay. That's an excellent question. How do you entangle atoms? Okay. That probably will take. Okay. In this website. Okay. So if it's easy to entangle atoms, like how you entangle atoms. Okay. There are different ways of doing it. For neutral atoms, the easiest way to entangle them is to use what's called the Rydberg atoms. The Rydberg atom. It's a Rydberg state. It's a very, very high-level state of an atom. So remember, we are using for strontium, for example, 5s squared. That thing would be like 5s, like 40p, very high quantum number. Okay. You have state 1, you have state 2, and then somewhere you have a Rydberg state. You are going to have a laser which excites this perfectly. Now, I'm going to switch to the quantum information designations. That what does it mean to be entangled? It means that you are building the wave function 1, 1 plus 2, 2. Or in principle, you can actually build also a quantum gate. So in this case, what you can do is to create some sort of procedure when you have two atoms, you connect them to Rydberg states. And you shine lasers in your atoms. So there are several laser pulses which eventually uses the fact that two atoms cannot be present in a Rydberg state. So if you have an excitation, then the one atom sits in one and another atom sits in Rydberg state. Then if you try to make it excitation, if it's in this state, then nothing is going to happen. But then if an atom is actually in this state, then this atom will actually get excited. So, and the reason this happened because there is a detune interaction. There's interaction between two atoms. And you can get an appropriate series of laser pulses, then there is a conditional restriction of whether the atom is allowed to go to Rydberg state or not. And the appropriate series of laser pulses will actually create the superposition. So in this document which I put about neutral atoms, there are actually specific laser pulses which tells you how to even make a quantum gate out of them. Because make a quantum gate, you essentially need to be able to precisely control this laser pulse. There's 3 laser pulses to make a quantum gate, and quantum gate produces specific quantum logic operation with atoms, which involves entanglement to a certain degree. But mostly all you do in this case, use Rydberg states, and you shuttle the population between the ground state and the Rydberg state, and because you actually have a prohibition of certain types of excitation, eventually you can make them entangled. Usually it's a few laser pulses to make them entangled. But it's easy to make 2 atom entangled. The more atoms you get, the harder it becomes. With the ions, it's a bit different. All ions, they're all sitting in the same trap. They're all sitting in the same motional trap. So what you're using is the fact that when ions are sitting in the motional trap, at some point when you make an excitation, this ion can go this way, but this one has nowhere to go, it's prohibited. So it gets stuck in this level, and that actually allows you to create the superposition. So all it is pretty much you just apply laser pulses and apply some clever interaction when you can make conditional. So if atom is in 1, it happens. If atom is in 2, not happens. So that atom gets stuck in that state, and that creates a superposition which you want. So there is many, many ways of doing it. There are many different schemes how to do it. So in general, now the superpositions for a few ions or a few atoms can be made nearly perfectly. But doing it in large numbers, that is difficult. Other questions? Sorry, I misunderstood your initial question. I thought you just how you get atoms in a trap first. It's a great thing that that's what quantum information has been doing for past 20 years. That's all they've been doing, entangling atoms and manipulating them with making very specific logical procedures. So now essentially using this volume of information, and this Rydberg dressing, that's one of the most common ones. Because, as I said, when atom is in Rydberg state, no other atom near it can go to Rydberg state. Because they interact so strongly, it detunes the laser frequencies. So it makes all the others stuck in the lower states. And this is Rydberg dressing is actually used for create spin squeezing in atoms. But not with this perfect one-to-one interaction. More you just create more of them, and there is a little bit degree of entanglement, but not perfect. Other questions? Okay. So, different clocks. So one way of different clocks is molecular clock. I'm just going to flash it for you just to show molecules are so different. Because you see, molecules have many, many different levels. So here you have one laser excites the molecule, another laser excites the molecule. Eventually you add with some sort of 2 molecular states, and you just essentially looking at the oscillation of those 2 states, look at some special molecular resonance to essentially make pretty much the same measurements. So as I said, the molecules usually require more lasers. They're also less precisely controlled. Also, not all the molecules can be laser cooled. People are getting there, and they think this experiment will get about 10 to the minus 17 per day. That's a strontium OH. It's a triatomic molecule. As I said, they will get there eventually. And molecules will give the best restriction to the electron coupling and the proton coupling. But the other idea is to build nuclear clocks. And that's actually one of the projects which I've been working on. Here are typical energies of nuclei. Here are typical energies of atoms. In thorium, it's like somewhere right here. It's only one. There is another uranium at about 89 eV, but there is nothing anywhere close. So for now, we are stuck with one system, which we can work with. So the reason why this works is for some reason which we really don't understand, the difference between the two ground states of the nuclear clock, it's about 150. Right now it's been measured to, I think, 148 nanometers. Lifetime is probably hour to a couple of hours of the transition. Since we are now back to nuclear physics, that cannot be computed accurately. So the reason why they want it is because it's much higher sensitivity to alpha aeration. It's sensitive to other fundamental constants. It's a fantastic clock. Because now you're exciting by a laser a nuclear transition, not the atomic transition. But remember, nuclear is very nice shielded by the electronic cloud. Right now we are not using electronic cloud. We are actually just using the nuclear transition. And again, it's extremely ambitious program to excite a nuclear transition by a laser. It's never been done before. So right now we don't have an operational version. We just found this transition, and people are working on laser excitation. And we believe in 5 years we actually have a working prototype. So it's a very well understood how to build better and better laser and get better and better frequencies. So all we need to do is to laser excite it, and then the progress be very, very fast. So there's a number of groups in the world which are doing, and European groups in Austria and Germany. And there's a few groups in the US. And there is groups throughout the world to do it. So there's no question this will be built. So the reason why we want it to build, it's because sensitivity to alpha variation scales as a frequency of the transition to the Coulomb energy difference. And we believe it to be on MeV scale because it's known that the Coulomb energy itself, it's in a GeV scale. So your sensitivity is automatically about 10 to the 5. And remember, best atomic clock has sensitivity of 6, and that's at 10,000, or even more. But most importantly, it also has sensitivity, about the same sensitivity to quark masses to lambda QCD, and for many reasons, especially for the relaxion, it's more likely to actually couple to gluon sector than to couple to the photon sector. And in this case, we think we will have prototypes in 5 years, which will already be comparable. In 10 years, we will have a high precision nuclear clock, and then we'll be much better by 5-6 orders of magnitude. So which other field can you improve by 5 to 6 orders of magnitude in a dark matter parameter space in 10 years? And just to show that's a combined plot from all the other experiments. Many things there. If you're interested, all the ultralight dark matter limits are actually compiled by CR and O'Hare. There is axion limits, but there is scalars and vectors. So let's see what's what. The Bacon, it's a Boulder atomic clock optical networks. That's the best current clock limit. And all of those not solid lines, those are projections. Now, this is naturalness if it's like for Higgs, 10 CeV. This is naturalness if the naturalness occur at electron mass. There is a hand-waving reasons why it could actually be at electron mass for the scalar. If your scalar is protected by symmetry, then it's natural anyway, period. So if that's naturalness limit, we are well within it as well. So those are the best existing clocks. This is equivalence principle emission in space. Those are cavities which will get much better. These cavities will eventually get here. This is actually a GO600. It's an old gravitational wave detector. Those are various optomechanical resonators. This is a MAGIS 1 kilometer. That's 1 kilometer interferometers. This is future interferometer in space, and this is actually a nuclear clock. A nuclear clock, our grant is about 13 million euros. So it's in millions, not in billions. Any of those would be in billions because they need to be in space, like a LISA type scale. So as you see, we think we'll get here within 10 years. So this is one of the best scalar searches which you can do. So any questions on this? And this is just F-mu coupling. On that plot, you actually also can see ME. And there is, in our recent paper, if you Google for my name, we actually have DG plots as well. So, but for DG, you pretty much need a nuclear clock as well for the gluon couplings. Any questions? But as you see, there's many experiments. So all of those are very new prototypes. This is spectroscopy experiments. This is the cavities, and cavities is the first experiment, so they will significantly improve. So as you see, you actually get in all the mass ranges. This plotted 10 to the minus 6. Actually, from the site, you can, there is just Jupyter notebooks. You can plot any range you want whatsoever. So it's very convenient. So all the ultralight limits, all the axion limits are there. So, and now